Okay, so let me also begin by thanking the organizers. Okay, so what I'll do is I want to describe some results that we have obtained with Priyanka on the critical dynamics of the jamming transition. So I'll describe what jamming transition is, but before that, let me start with something simpler. And the simple model goes by the name simple exclusion process. So what you have to think about is just a ring with L lattice sites, and each site could be occupied by a particle or a hole. So what happens? So here's a sort of diagram. So a particle attempts to hop to a neighbor, to a nearest neighbor, with a constant rate, and so this guy can hop, but let's say this one cannot hop. If I allow particles to move only in one direction, so then I call this a totally asymmetric case. Okay, so this is a very simple model, and the stationary state is known exactly, in which all configurations are equally likely. So perhaps the more interesting thing in this model is to ask for the correlation functions, the dynamics of the correlation functions. Okay, and today I'll talk about particle or density correlation functions in the stationary state. So they are just defined the usual way. So this is the quantity S of RT, which is this Ni0 denotes the occupancy variable as site I at time 0, and similarly the other one. So this is a sort of central object. Let me first describe the results, the known results for this TASEP model, because it will set the stage for what I want to say later on. Okay, so this is a simple model, and it's useful to consider the mapping of this model to an interface growth model. So you already heard a bit about it in the previous talk, but let me anyway describe it. So the idea is that you have this lattice gas model, the TASEP model, and whenever a site is occupied, you put the up tilt. For an empty site, you put a down tilt, and so on. So when a particle hops, then you say valley has become hill, and so on, with the rate 1. Okay. So this interface growth model, the height, the profile, it obeys a famous equation in which you have the usual diffusion term, there's a noise term, and there's this nonlinearity, dh by dr square. The coefficient of this term can be calculated using the steady state current of the lattice gas model. So if I know the steady state current of my lattice gas model, I could construct the height profile correspondingly by calculating this lambda. Okay, so I'll connect these two in a minute. Okay, but let me stick with this interface growth model for a second. So just like for the lattice gas model, we had a correlation function. One could define a height correlation function also, which is known to be of a certain scaling form, given by this. Here we have two exponents, alpha, which relates height and the distance, the spatial scale, and there is other dynamic exponent which relates space and time. Okay. Now, the exponent alpha can be calculated using equal time correlation functions, and it's sort of very simple calculation. It turns out to be just half. The dynamic exponent, there are different ways of doing it, but basically if you look at this KPZ equation, it has a special symmetry which allows you to find the exponent z also, and that turns out to be 3 by 2. So the reason I'm telling you all this story is because the object of interest, namely the space-time correlation, the correlation function for the lattice gas model is related to the height correlation function according to this relationship. So since HRT had this scaling form, this one, the first line, I could write down correspondingly the scaling form for the density correlation function, and knowing these exponents, it turns out for the TASEP, the autocorrelation function decays with as a power law in time with the exponent 2 by 3. Okay, so this is all well known. Okay, so the model that I really want to discuss is also defined on a ring. Again, each side can have either a particle or a hole. But the difference from TASEP is that the hop rate of a particle depends on the number of vacancies in front. So for instance, this guy hops with a rate u of 2 because there are 2 vacancies in front. Similarly, this guy hops with a rate u of 1, and this one is not allowed to hop. Okay, and you can choose various rate choices you can make, and a particularly interesting one is this one, in which the hop rate decreases with the increasing number of vacancies. And there's a parameter b sitting here. If b is 0, we go back to TASEP model. When B is not 0, this last term kicks in. So let's just imagine what is the meaning of this rate choice. What does it do? So imagine the following. Suppose you have a system at a very, very high density. I mean, very high meaning close to 1, let's say. So the number of holes would be very less. Okay? So then, since the interparticle spacing is very small, this last term really doesn't kick in, the B by N term, because the spacings are tiny. Okay? Whereas if you're at very low densities, then suppose a particle by fluctuations creates a large gap in front, largest gap in front, but this particle will move even slower and slower. So it's going to promote the formation of the gaps. So one could, so qualitatively, one could expect a change, a phase transition in this model. And in fact, it has been shown that for the parameter B larger than 2, a jamming transition occurs. So let me just show you a picture of that. So here space-time plots. So as I said, for high densities, the white spaces, that's the whole cluster lengths, they are tiny, order 1. But at low enough density, there is a large gap of order L. It's a macroscopically long whole cluster. Okay, so this is a phase transition that occurs. And at the critical density, the whole cluster length is sublinear. Okay. So the question that we are interested in is what is the autocorrelation function or the density-density correlation function at the critical point of this jamming transition. So that's a basic question that we were interested in. Again, just like for TASEP, we could map this model also to a height model and try to basically see if we can use the same machinery to say something about the autocorrelation function here. And just like for TASEP, this was true, that it decays the power law with 2 exponents, alpha and z, and one is asking, do these numbers change at the transition point, at the critical point? Do they change from the TASEP answer? Okay. So before moving to critical point, let me just say what happens in the fluid phase. So fluid phase is the high density phase in which the interparticle spacing was of order 1. So we don't expect any funny thing to happen there, and I expect that TASEP answers should be valid. That means the autocorrelation function should decay the power law with an exponent 2/3, and that's what is consistent with numerics as well. So let me go to the critical point then. Okay. So I said for TASEP, you could calculate the 2 exponents alpha and z. Alpha we could calculate using the static correlation function, equal time correlation function, and let's try to do that in this model also. Okay. So there are a few steps involved, and I'll just tell you the answers. So what we can do is, so we have this exclusion process. We can map it to zero range process, for which many properties are known. Using that, one can first calculate the equal time correlation function for the density one, for the exclusion process. Then using this relationship, between S and H, one can also calculate therefore the height correlation function. I'm not sure to get this. Okay, so anyway, so the height correlation function now has 2 terms. The second term is the familiar term, is the linear term, which gives alpha equal to half for the TASEP. But you see, there is one more term which is extra and new term. The first term, the r to the power 4 minus b term. The point here is that we see that the exponent alpha changes in this model. For b larger than 3, the second term is more important, and therefore we get the old TASEP type alpha in this case also. But for b between 2 and 3, we have an anomalous roughness exponent. It's 4 minus b by 2. So the point here is that the alpha varies continuously with b in a parameter range between 2 and 3. Otherwise, it's just half. And it's half when the density-density correlation function is decaying as 1/r or faster. So remember for TASEP, this density-density correlation function is 0. But here I'm saying if it decays faster than 1/r, you still get alpha to be half. Okay, so this is the story about the alpha alone. But what about z? Okay, so z for TASEP, we could appeal to the KPZ equation, and it had a special symmetry which allowed one to find out the z. So we tried to do the same thing here, but remember I also said to set up that you need second derivative of the current. The problem here is at the critical point, depending on when we approach the critical point from the high density or low density side, we find that the derivatives are not continuous. So we don't know how to set up this hydrodynamic equation. So the derivatives are not continuous, and that's what enters the hydrodynamic equation. So right now I just don't know how to sort of find Z analytically. So that's something missing in our understanding here. But we conjecture that it does not change. It remains the same as TASEP, and Z is just 3/2. Okay. So let me just buy that and go ahead and see if that works. Okay. So here is the simulation results. So for B larger than 3, alpha did not change. It was half. So indeed we find, so therefore the answer should not change. It should be 2 or 3. And the points are from simulations. And this green line is 2/3. It doesn't look great. It sort of approaches it, but it's not quite good. So what Priyanka realized was that actually the corrections to this, which we know using the static correlation function, if you include that also, then she is able to find a great fit. So the point here is the leading order answer does not change for B larger than 3. But for B between 2 and 3, the leading order answer is different. Autocorrelation function changes, decays the power law, but the power is continuously varying. And this decay is slower than in TASEP. Okay, so that's basically what I wanted to say. So I described to you only one model, but basically you could repeat the same story for other models of jamming transition. So I chose the rates to depend only on the number of vacancies in front, but you could choose also rates that depend on the number of vacancies in front as well as back. You could also work with models in which each particle has a different hop rate. So for all these models, basically everything can be done in a similar way, and we get basically similar answers. The roughness exponent is different, and for dynamic exponent, we don't have any analytical understanding, but we believe that it does not change from 3/2. So here is the sort of one-line summary. So the point here is a simple point that I'm trying to make here by studying these various models is simply this. If the equal time density correlation function decays faster than the inverse distance, then autocorrelation function remains the same as in TASEP. Otherwise, if it's a slower one, then you may have a different answer. And in these models, we find it to be continuously varying. So there's an obvious open question: how to set up a hydrodynamic equation? Can it be done? But I mean, I don't know. But your feedback is welcome.
In the KPZ equation, alpha plus Z is 2 because of alpha plus Z
is 2, yeah.
Because of some
right. Yeah, so here it's violated.
Well, how? Because the mapping you showed, where does it fail?
But I mean, I don't know if it's the KPZ equation is still valid. So I'm not able to see that.
For lambda finite, if the lambda becomes infinite, be equal to 3 or something like that.
No, it's not about lambda being lambda can actually be 0. It can be infinity. We find various values for it, and it's not clear whether it's really the correct equation. So I mean, I'm skeptical that it's KPZ, but somehow Z still remains, I think, 3/2. I don't have an understanding of that.
Join me.
Thank you.